In this video, we will discuss telescopes. Our discussion of telescopes will be our final optical instruments. We talked about cameras, we'll talk about eyes, we talked about microscopes, and I'll end with telescopes. At least the optical instruments that are making images as their main purpose. Now, there are really two types of telescopes designs. The main one we'll talk about is something called a refracting telescope. A refracting telescope uses two lenses. There's also something else called a reflecting telescope, which uses a mirror and a lens. Now, the idea behind a telescope is that you want to provide a large angular magnification, just as with all of the other devices. But the problem in this case is not like for the microscope where we want to do even better than the compound or the simple magnifier. What we have here is that the object is very, very far away. That's the goal of looking using a telescope, is that you want to hold a microscope and look at something far away. So the problem is that we can't even use a simple magnifier. Because remember, in order to make that larger virtual image from a converging lens, which is what the simple magnifier was, the object itself had to be within the focal length. So if I'm in the case of like a stamp or something like that, it's pretty easy. I just move my lens and I put it right on top of it. But if that's a mountain on the distance, I can't just take my simple my magnifying glass and then put it within an inch of the mountain. That defeats the purpose of a telescope. I'm supposed to want to look at the telescope from far away without actually going over there. So how do I make an image that is larger and virtual? Because that's what I need in order to see a upright image from it. And I want to be able to see an enlarged image as well. Note if it was, I had just looked at it through the original magnifying glass, it would be, since it's so far away, you'd have a very, very teeny image that was at the focal point of the simple magnifier. So that's not super helpful because seeing an upside down and very, very teeny image, like projection onto a screen, for example, isn't very interesting, basically. So how do we actually get this to work? Well, a solution is to have two converging lenses, just like with the case of the microscope. But the purpose here is slightly different. Here, the first lens is simply to make a nearby image. So my object is very far away, and I'm going to make the image get close to my face by having the object sort of get close to my face by having that first image appear very close to my face. And again, what we'll do is we'll place that image at the focal point of the eyepiece. Again, we have the terminology, the objective lens is the one that's towards the object, and the eyepiece lens is the one that's near the eyepiece, so that the image, the final image, is very, very far away from my face, so it's easy on my eyes. I can't really draw that very easily on this diagram, so I drew the final image being not terribly far from my eyes, but in reality be very, very, very far away at infinity. I'm going to, again, the basic idea is I have two lenses. The first lens makes a real image. The second one makes a virtual image of it. And the reason I make that first image is not to magnify it, because it's going to be way, way, way smaller. For example, if you look at a mountain and it makes a little teeny image of a mountain nearby your face, the height of that mountain, that image is much, much smaller than the actual mountain, which is maybe thousands of feet tall. But it'll at least bring it close enough that I can look at it with my simple magnifier. That's the idea of the first one. Now, what we're going to do is we're going to have a different definition again of magnification. Again, it's an angular magnification, meaning it's a ratio of two angles, and it's how big it looks to me in one of two scenarios, and it's the ratio of those. So the numerator is the same as we've been doing before. You look through the device, how big is it that you see it, what's the angular size it has when it's comfortable, so that if that image is very, very far away. So your eye is relaxed, how big can it be? That means your eye is going to be right up on the eyepiece again. But the denominator is actually a little different. The denominator is the actual angular size of the object. Okay, so it's not like if you went up to 25 centimeters from the mountain and then said how much of my field of view is it. It says right now, if I'm looking at a mountain, how many degrees does it look, how tall is it, from my point of view, and if I look at it through the telescope, how many degrees is it in that case? So it's now the object doesn't move in this case, whereas in all of the other cases with the simple magnifier and the microscope, the way it was defined, you move the object between the 2 points when you compare it. This is literally sort of the straightforward angular magnification. How many times larger does it look to my eye if I look at it directly or lift up the telescope and look through the telescope and see it? And the way you find it is it just depends on the two focal lengths. So it's the focal length of the objective divided by the focal length of the eyepiece. Simple as that. Um, so if you have a large focal length objective and a short eyepiece objective, then you're going to have a very large magnification. Now, this doesn't directly have any length involved in here, but note there's a certain distance you need to place these lenses away from each other. Since the object's very far away, the image from the first lens, the objective lens, shows up at its focal point. And in order to have the image from the first lens to create a second image, the final image, that is very far away again, so your eye can see it nice and relaxed wise, then that first image has to be at the focal point of the eyepiece lens as well. So when this is actually designed, the two focal points are at the same location. So the distance between the lens is the sum of those two focal points. So if you have a really large objective lens focal length, in order to get a really large magnification, you'd have to have a very long telescope. And so in terms of design notes, what you really want is a very, very small focal length eyepiece lens, because that'll make you have, that can increase your magnification quite a bit without increasing the length quite a bit. One thing to note about why it goes in this way, the stronger the focal length, the smaller the focal length of the eyepiece, the more powerful the eyepiece lens is. So that leads to a larger angular magnification just in that second part of the process. The image from the original objective lens, the size of that depends on the focal length of the objective lens. And the bigger the focal length of the objective lens, the larger the image you form at the first image you form. So that's why you have a larger magnification, is that first image is bigger if you have a larger objective lens focal length. This is a much simpler formula to actually plug in. One thing to note here is that since this is the ratio, if you flip FO and FE, so you interchange your objective and your eyepiece lens, the magnification doesn't stay the same, it flips upside down. So a 1/2 would become 2 and vice versa. Whereas in the microscope, if you switch the two focal lengths, you end up having the same magnification. A reflecting telescope makes that very first image with a mirror. So instead of making the first one with a lens, so now having your objective was a lens in the first case, here your objective is a mirror. The advantage of it is that it has a much larger collecting area. It's much easier to make a very, very large mirror than it is to make a very, very, very large lens. And the size of that lens or mirror determines the amount of light that is coming in. If you're looking at something very, very dim, like a very distant star, you need all of the light you can in order to make an image. The brighter it is, the less time you have to spend looking at it to collect more and more light. So in practice, most actual telescopes like the Hubble telescope and all these famous observatories are actually use reflecting telescopes, because they're just much easier to make a large mirror on that surface below than it is to form have a great big lens on the front.